Thank you for the invitation. So I'm a postdoc researcher at the University of Cambridge in the structures group, and I'm working on automating construction, but as Enrique said, I will be presenting the research work I did during my PhD at École in ETH Zürich. So I will be talking about exploring topology of architecture structures. So what I mean with architecture structures is, the best way to describe it or to illustrate is to show what everyone did and what everyone presented earlier on. So I think you are actually a great audience for this talk, and as you all spoke about geometry and topology, I'm sure we'll have some interesting discussions to conclude this. So let me start by introducing my research on topology finding, as I coined it. So during my master's thesis that I did at the Bollinger group in Zurich in 2016, I had the chance to contribute to the exhibition at the Venice Biennale, where we produced this piece that was meant to demonstrate the potential of funicular form finding. So funicular form finding, you're probably aware of this, but it's a strategy to generate compression-only geometries that are suitable for masonry vaults or concrete shells, for instance. And here the presented approach, so thrust network analysis, actually relies on graphic statics. So you have a form diagram in the center that shows the layout of the forces in your structure, and the reciprocal diagram at the bottom that will give the magnitude of forces to be in compression-only equilibrium and get a funicular design like this. And so the primary input of this form finding strategy is actually the topology of the form diagram, so in the middle, which will actually drive in the following design steps. So it will either enable you to get to the shape you want, or actually block you from achieving this. So what I had to do was to develop a strategy to generate these virtual force patterns that could accommodate different features, such as a set of boundaries, the inner holes, the creases that you might want in the structure. And so that was my first work on exploring the topology of patterns for structural design. But still, it applies to, let's say, material patterns. So I worked mainly on the surface structures, so it can be masonry vaults, concrete shells, cable nets, grid shells. And well, for these structures, what they have in common is that when you design them, geometry is important, but this is driven by topology. And so I think that topology is actually more important, or it's actually the earliest design step, and that will enable you to design the structures in an efficient manner or not. And especially their singularities. So I take this example of a knit, which is a concrete shell stiffened by this corrugation pattern. It's actually the record for the largest span for concrete structures, and that's mainly due to the singularities in pink. So you can see that you have this regularity in the corrugation patterns, but what's more important are these irregularities that allow you then to break this pattern into different patches and to orient these stiffening corrugations in the right direction, so to carry the loads towards the support. And if you don't make a relevant choice of singularities on this design, then you will not be able to bridge this span. So in the field of structural design, also computer graphics, the main approach for the generation of the singularities comes from field integration, as you did for curvature. So that process will give you this quad mesh from a cross field on a surface, and the singularities will come from the areas where the field is not mathematically defined. And I'll use this example from Schiffner and Balzer, where they explore the design of a quad mesh pattern for the British Museum, and they compare two strategies. So the topology on the left actually stems from a stress field. So the beams are aligned with the load paths that provide structural efficiency. And on the right, the topology actually stems from a curvature field. So as you know, the beam will be aligned with a curvature. That will give fabrication ease in terms of curvature of the panels, for instance. So they fundamentally differ by their singularities, because the geometry is the same. They map the target shape of a British museum. But each design is optimized for a different objective, but there's always a question of which one to choose. And actually, the designer has to take into account both structural efficiency and fabrication ease, among the many aspects that come into play when one designs an architectural object and has to build it at a large scale. And all of these constraints evolve during the design process. So beyond this topological optimization approach, my strategy is to actually provide the designer a means to explore topological design spaces in order to find trade-offs between these multiple objectives. And that way you can design a structure that is elegant, efficient structurally, but also affordable in terms of construction. So you have to take all of this into account. So if you just have an outline of the research objectives, so with topology finding, I'll be tackling topological design spaces, providing algorithms for it that are complementary to form finding and topology optimization, but they're meant to be topology finding algorithms compatible with the geometrical design approaches that we're familiar with, informed by optimization, and have the possibility to actually use different performance metrics, so you have a flexibility in how to evaluate the performance of different designs. So here's my approach to deliver on these objectives. So I focus on quad meshes, which are, as you know, a mesh with quad faces. So why? It's because quad meshes are the natural generic manner to represent 2D objects like surfaces. They provide this regularity that's extremely important in structural design because of aesthetic, statics, and fabrication reasons. A non-structured mesh would not provide these features. And we focus on the singularities. So you're all familiar with this, so I won't spend too much time explaining it. So they'll all be highlighted in pink throughout the presentation. And I will be using the British Museum as a key example to illustrate my work. So you have the Richmond surface, and I'm using the British Museum. And I will be using quad meshes and in a system agnostic approach, sort of. So you can see the faces to be voussoirs for masonry, or you can see the edges to be steel beams for grid shells. There's a flexibility in the structural system that's being represented. And so because the singularities are actually depending on the topology, it allows me to decouple the design from geometry in order to focus on the specific data that regard the singularities in this coarse quad mesh. And so as such, geometrical design and density optimization and other local topological operations can be performed independently. Be compatible with topology finding, which so focuses on coarse quad meshes. Because quad meshes are generic objects, you can still apply different patterns on it. So I will just mention the Conway operators that will allow you here in that case, for instance, to get a pentagonal or triangular or diagonal mesh from this initial quad mesh, and that will give you this equivalent singularities in pink. So I will present 3 encoding strategies for different methods in topology finding. So I will start with the most intuitive one for the designer, which is geometric encoding using geometrical objects. I will move on to graph encoding for topological rules, and I will conclude with this string encoding using alphabet operations, which is the most generic approach that's suitable for a computer as opposed to a human. And so this work is implemented in a package that's open source. So because the goal is to actually share this research through user-friendly tools. It's based on the Compass framework developed at the ETH Zürich. So let's finally start with the core of the matter, so topology finding, and with the first strategy, which is based on geometrical input. That's included because the designer only has to play with surfaces, curves, and points. So if, again, we revisit the pattern of the British Museum, there are several design features that are important that you might want to integrate. So they are the topology of the boundary. You have this rectangular boundary and this inner circular boundary that you might want to align neatly, as done in the original design for aesthetics reasons and fabrication reasons. Regarding geometrical aspects, you might want to integrate the fact that you have these slight creases close to a support that stiffens the shell, so you want to probably align your pattern element along it. And if you think about also a static system, so you have a thrust that's concentrated only at the corners, so you might want also to orient or concentrate all the pattern elements so that they would carry the loads toward these corners, which are the stiffest part of the structure. So these are all heuristic features, and that could be integrated in the design of a pattern or its topology. And I will present you a method you mentioned before, now to integrate this, so which is using the medial axis of a shape, also called the topological skeleton, and so which is actually a shape recognition technique that performs this dimension reduction. So you can see here we see it from the top view, but it's a curved shape that's been mapped to the plan. So from the surface in red, you get this topological skeleton in pink. And here I designed a set of transformations to go from this topological skeleton that will provide you a decomposition of a shape that doesn't still give you a quad mesh or coarse quad mesh. So what one has to do is to remove extremity branches with some pruning, and then from this intersection of the different branches, add these new branches to graph them so that they connect the singularities to the closest boundary. And then, discarding the actual curvature of the branches of a skeleton, you can get the coarse quad mesh, and then following your favorite design process, from finding algorithms or whatnot, you can densify it, smooth it, and you obtain this quad mesh pattern where you can see, in gray, and where you can see in black the coarse quad mesh, and the singularities in pink. So what's interesting with this approach is that even though it might be intuitive for simple shapes, if we have a look here at the project in Germany, if we revisit this timber roof, here you can, split of a second, just get this topology in this mesh, which is less intuitive and probably quite tedious to draw by hand. So here you have 38 singularities, which would require a bit of care and experience from the designer. So I handle the boundary of a surface, but I mentioned other aspects of heuristic features. So following a similar approach, one can include point features. So here in that case, I mentioned the fact that you have thrust only at the corners. So here there's this additional rule that will split the quad into two triangles, which are actually pseudo quads. So you can imagine it as a quad with a very short edge, where you have this point feature in order to form a pole point at the corner. And as such, you have this concentration of the forces at that location. And also the curve feature. So I mentioned the creases in the shape that go to the support. So here you can actually split it. I mean, add this line that will change the topological skeleton, and there, following the same procedure, can get a more complex coarse quad mesh, but then you can eventually obtain this this dense quad mesh where you can see that the edges are neatly aligned, or they actually rebuild this input curvature, this heuristic designers. And so if we apply it for British Museum, so we have kind of different designs without curve features, which we'll take as a reference. So here, for all of them, if we speak about, for now, just about structural efficiency, and after some optimization of cross sections, if we take a design without any features, we get this reference weight. And if we compare it with the design with the curve features, though we wanted to, the heuristic was to add it, but apparently it actually worsens its performance. But if you actually integrate the point features, so by attracting the beam elements towards the support, you can actually reduce by almost 40% the structural weight. And then here you can see that what's important is to have these point features. Whether you have curve features or not is not important regarding structural behavior. But because structural design is a multi-objective problem, you might want to choose whether you want to have just a few nodes with 6 beams to connect, or twice the amount of singular nodes, but with only 5 beams to connect. So then that's up to you to decide and continue from there. So here I presented a method for geometry encoded topology finding. So there's this high-level approach that's intuitive for the designer because you're only playing with a surface, its boundary, and curves and points on it, and that's that follows a heuristic approach. So as I shown, you might make good guesses or bad ones. But the challenge is that here you don't have a direct control on the topology. So you cannot explicitly change the relation between the singularities. It's done only through geometrical objects. So that's why when I moved to a second approach, which is graph encoding. And for this, I'll be using a rule-based expression using grammars. So if we have a look at these sketches from Jörg Schleich, he explored different sets of designs for the bridges, but at this level of conceptual design, he did not just vary the height of the masts or change the number of cables. He actually played with the connectivity of elements, so the topology. So that's what was the most important aspect to consider at these early stages at the competition level. This pen and paper approach can be computation enhanced, so using grammars that encode these all these intuitive design rules. So that's what Caitlin Müller did as part of her PhD, which is to develop a grammar, so a structural grammar to generate the design of bridge designs that cover different typologies, so not topologies, typologies. The structural grammars are actually part of a wider family of shape grammars that were developed by Steiny and Gibbs, and they have found applications in engineering, but also in architecture, urbanism, and art. So there's a wide range of possibilities coming from this grammar rule-based approach. And so for my design, so I have to develop a quad mesh grammar that would allow me to explore the topology of the quad meshes, or coarse quad meshes, trying to use a minimum number of rules for computational simplicity. So to do this, I actually identified a fundamental strip structure in quad meshes. You can see them in blue on this simple layout. So these strips are purely topological, so they connect the pairs of opposite edges across faces, and that goes through all the faces of a mesh. And then from this, because these elements are a fundamental aspect of a quad mesh, I developed this low-level grammar with only 2 rules. One that adds a strip, so taking the set of edges or poly edge in blue, can insert a strip, or you can have the reciprocal, the opposite rule to delete the strip. And you can see that this will actually change the connectivity between the different elements and create or cancel out singularities here highlighted in pink. So if I come back to the core squad mesh for the British Museum, so that would be the one you would get from this from the medial axis, from the previous method. If you say add a strip along the boundary poly edge, you can see that you get this new organization between the singularities. Even if you say delete the green strips, you get this new type topology. So you can see that with just a couple of clicks, you can get different core squad meshes where you explicitly select the mesh elements. So this is the result of one of my open explorations to obtain different topological designs. You can see that the 4 designs that I presented before are included in this set, and I lost in that one, well, yeah, previously. And so here you have this, with just a couple of clicks, you can get this wide family of designs. So then how to explore, to compare them or decide on which ones are relevant or not. In that case, we integrate several statics metrics on deflection, stresses, and buckling, and also metrics on fabrication, so curvature, skewness, and the edge length variation. And here in that case, what I used was a self-organizing map, which is a strategy for dimensionality reduction, because there you have this 6-dimensional performance space, and which is not really easy to see in as a person. So that's why then you can map it to a 2D space, which is easier to see. So what the self-organizing map will do is to organize the different designs in this 2D space, such as the designs with the most similar performance are the closest. So you can see, as such, you get clusters. So we can have a look at this cluster of 5 designs. You can see that it will actually be similar. They will have this low stress utilization, low panel curvature, and high edge length variation, for instance. So there's a similar performance. But what's also interesting is that they also share the fact that they have this pole concentrations at the corners. All of these ones don't, for instance. And so that actually highlights a relation between the performance similarity and topological similarity. And so that's what will that's what drove me to explore or to test the next method, which is to inform the similarity, based on similarity, inform the topology finding process. So if we have a look at, if we leave the British Museum for a moment, we can have a look at these two different systems. So on the left, you have a Waffle Slab, which is a modular construction system, so super efficient to build, but it's not informed by statics conditions. So that's why you need this reinforcement around the columns against punch through, against shear forces. On the right, you have, on the contrary, the slabs from Navier that follow the statics isoline. So you have this optimized load path that makes it efficient. However, here you need this custom fabrication. So here you have really two extreme designs. However, as I said before, we need to think about all of these aspects. So the question is, by knowing a good design for for different metrics, how do we actually find a actually find a performance trade-off that will give us something that's somehow efficient and somehow buildable? So here, my approach is not for a trade-off to find a design, but to actually assume that a design with similar topologies have similar performances. And so I have actually this new surrogate problem, which is I will find a topological hybrid. You can see on this design that this has a similar topological features of the design on the left with this regular quad grid, and the features from the design on the right with this pole point at the corner. And then we assume that it will provide us some kind of a performance trade-off. So it's not so much so far-fetched. It's actually the approach of genetic algorithms when one will, over multiple iterations, one will recombine designs that perform well in order to move further in the process. So that's the idea behind this, to use topological similarity to find trade-offs. I will just brush on the method. So assuming that we have two here abstract input meshes, so how do we actually find topological hybrids? So to do so, one has to define what is the similarity, so the topological similarity between quad meshes. And so in that case, I define it as a largest strip structure, so the strip structure that I introduced previously, that they can have in common. So using the design grammar, if you want to apply minimum number of rules, you can actually delete this strip in pink and these strips in light blue and orange. And here eventually you get the same design. So you have this something that I call this intersection submesh that only has the similar strips from the two input meshes. And then, since you deleted these strips that were not shared by these input meshes, you can add them back together using the addition rule. And then you get this union supermesh, which has the similar strips, the blue one and the red one, and the dissimilar ones. So this one has like all of the topological features of the input meshes. By playing with a combination of these deletion and addition rules, you can find these different intermediary meshes. So I'll stop this explanation and show a specific example. So imagine you want to design a grid shell for this pillow shape made from an arbitrary NURB surface. So here it has to take a self-weight, so a mesh load, and a point load, and it's while being pinned only at the four corners. So here in that case, so the different performance metrics, I will use heuristic design. So here I have one mesh that has this classic grid that's good in terms of variation of edge length, which could be an interesting performance metrics for fabrication. Here, because you have a support condition, so the grid shell is supported only at the corners, you might want to have this pole point here, as we've seen before on the British Museum example. So that's another coarse quad mesh can have that will heuristically, I imagine, have a low strain energy for mesh load. But because you also have to take into account the point load, so here you have this pole point that will provide many load paths, so many through the beams to carry the point load toward the support. So, and to hopefully get a low strain energy for this load case. And so now if you, for representation purpose, I will map these three heuristic designs to different corners of the map, and using this strategy that I briefly explained on finding the similar and dissimilar strip combinations. So you can get all of these designs that have different topological features. So you can see that all the designs at the top have the strips in light blue, but none of the ones at the bottom have it. So that's how it's organized. And then, so in that case, after dealing with the topology, you can run it through your densification and mapping or form finding process. And you can get this different designs. So here you can see that all of the designs at the bottom left have these poles at the corners. And if we evaluate the three performance metrics that I mentioned, we can see that actually the heuristic decisions that I made were good. This design has a very low edge length standard deviation. This design, it actually has the lowest one. This design has actually the lowest strain energy for the mesh load, etc. And what's interesting is that the design in the center, which combines all of the features from the regular grid, the central pole, and the corner poles, doesn't perform the best for any of the performance metrics, but it's not the only one. So depending on the specific project goals, then you can choose maybe to go for that design if strain energy for point load doesn't matter too much, or for that one, etc. It's up to the designer then to decide and explore further. I just show this example, which so that one is my detail in my thesis. So here I consider 4 metrics to design a tessellated dome with an elliptical boundary. Here there's a combination of funicular form finding and then a rationalization with planarization. And you can see that even for a very simple shape, you actually can get into fairly complex topologies, which are not just complex, but some that are efficient for some of the metrics we're exploring. So that actually shows that by combining simple topologies, we can actually combine them and breed them into this large family of designs. As another example here, in that case, I'm not using designs from two different performance metrics, but two different load cases. If you have a look at a flat slab supported on the 4 corners, and you have a look at the isolines for symmetric loading and for asymmetric loading, there's a bit of work on how do you interpret these isolines, as I'm sure you've experienced with your projects you presented earlier. And then you can actually apply the same strategy to get all of these combinations. That's actually just a sample of it. I'm not showing the performances because actually here in that case, you don't get good results because it depends a lot on how do you go from this interpreting the topology to actually getting a final design with specific density and geometry. So it's not as neat as it sounds, because performance eventually does not depend only on the topology, but also the other aspects. So I presented here requirements or objectives that were important to minimize. And however, sometimes you have hard constraints that you need to apply to a topological design, so which means that you have to fulfill a requirement, like maybe on the specific valency of the node. And I will present one of it, which I call two-color constraint. It applies to a variety of structural systems. And I will focus on foliage shells. So if we have a look at the British Museum, so with the support conditions, with thrust at the corners only, and the previous results that we got, it seemed that it would make sense to actually have this maybe a corrugation pattern, so stiffening the shell to carry the load towards the corners. That actually corresponds to the knit, a structure that I that I use at the beginning, so the largest span concrete shell, which follows which has similar constraint on the support conditions. However, whereas for the knit, we can actually do this folding. So if you have a look at the coarse mesh, you can say that directions in red, the strips in red are continuous, and the ones in blue are folded. You actually cannot do it for the British Museum if you use that coarse quad mesh, which actually comes from the medial axis, because you can see that, because here on this vertex, with a valency of 5. So you have 5, so an odd number of strips that go around it. So you cannot say have continuous lines in red, for instance, and folded lines in blue, because you have this third color, so in green, that actually messes up with your system. So you have to be, so what we will explore now is how do we actually find a coarse quad mesh that follows this 2 color constraint. And here, in that case, to be able to fold the British Museum. But it applies to other systems. So it applies to nexoid structures, for instance, where you have this alternation between nodes that rotate towards the left, then towards the right. Or elastic grid shells, where you want to define a direction of beams that will be at the bottom and some that will be at the top, in order to avoid this weaving of the beams and get this necessary bending. And so all of these properties are actually fit within these 2 color constraints. So whether it applies to the nodes, the faces, or the continuous edges. In that case, I will explain how do I solve it specifically for solid shell, but it's exactly the same approach for different systems. So I mentioned a problem of 2 colorability. Why this name? Because it's actually a common problem in graph theory. And so to use the existing algorithms, I have to encode the problem that I have into a graph. So here I'm using so it's about the coloring of the strips in red and blue. So I'm using the different connectivity or the different overlaps to get this strip graph on which I will explore whether the design can be 2-colored or not. So if I just show it on this example, which cannot be 2-colored because we have this 5 valent node in a third direction in green, you have this non-2-colored strip graph, so which means that you cannot have you cannot use only 2 colors for the nodes without having nodes of the same color not connected. So if we were to say this node is red, the requirement will fail because it's adjacent to this red node, and the same for blue, it's already adjacent to a blue one, so you have to use a third color. What's the best way to make it 2-colored? You just basically remove that node. And what does it mean in terms of grammar rules to apply? It actually means that you can use the strip deletion rule to actually remove a corresponding node of a corresponding strip in green. And as such, you get this quad mesh topology with only 2 colors that could be folded. There's actually a very large set of possibility to color graphs with 3 colors. So I won't dive into the details, but I developed some kind of search algorithm that will try to find all of the different combinations that are not redundant with each other, so that will give you different design solutions. So if we apply it to the British Museum topology, you can get these 5 designs, these 5 coarse quad meshes. So we'll give you these 5 different patterns, so you can see from the similarities in pink that they all differ very much, and you can still use these 2 colors, red and blue, to be able to fold the design. So because you can choose whether you fold it in the red or the blue direction. So you have 5 designs times 2 directions, so that's 10 possibilities to fold the British Museum. And here with some structural analysis, one can actually, if you do the calculation, you can see that if you don't fold it in the right direction, the strain energy will actually increase, can increase a lot. But if you do it in the right direction, you can actually reduce the strain energy by 3, so which means improving the efficiency of your design by 3, if you do it in the right direction. So just to conclude on this graph encoded topology finding, so here what it allowed us to do is to have this comprehensive expression. So we're allowed to explicitly edit any quad mesh topology and get any design. We could use uniform expression to find a multiple objective trade-off based on the similarity of the designs. And just now with a two coloring constraint, we're able to reduce the design space, so this gigantic design space, to just the ones that are feasible for, in that case, a specific system, which was solid structures that applies to a wide set of systems. Here, one of the limitations was that for the last two topology finding algorithms that I presented, the design space that you're exploring is somehow limited by the input that you have. So you're not discovering it. So you have actually this bound and this limitation in that sense. And so that's why I actually developed a third strategy, which is string encoding, that allows you to use a state-of-the-art solvers and algorithms. So to do so, before I was playing with, let's say, the phenotype of a quad mesh, so the actual connectivity that you can see on the left. But what an algorithm will do is not select a node. It will actually compute like a vector or genotypes of binary numbers or string of characters to use it as like some kind of the DNA of a design, and then you can apply genetic algorithms or machine learning strategies and so on. So this is the goal of moving from the mesh space to vector space, which is to use all of these state-of-the-art solvers. So to do so, I use something that's called turtle graphics, that's used for educational purpose to teach programming, where you have this turtle that moves around, being given orders to draw shapes. So these orders can be a set of words that tell you to go down, forward, rotate, change the color of a pen, etc. So this approach relates to a grammar. So it's actually not a shape grammar or mesh grammar as I've shown previously, but a formal grammar where you have this alphabet that encodes the rules. And this can be used, or this was used to draw complex shapes, so called L systems, for instance, developed by Lindenmayer, where he was exploring how to describe the growth of plants to use this using this descriptive model where he would change the set of parameters and the set of rules. In my case, I'm interested in editing the topology of a quad mesh, so which means that I won't be drawing freely on a blank piece of paper. So what I'm actually doing is using the quad mesh structure to move from one edge to another in order to select the different elements and to apply the rules of the grammar that I presented. So I basically have 4 operations, 2 for movement, one that will have a marker, a move, so pivot around vertices, and one that will have it turn around faces. That way I can visit all of the edges in a mesh. And 2 more rules to actually apply the grammar rules that I presented before. So if you use this rule, so you can start by saying, I want to start collecting a poly edge, so I can add a strip. So you start selecting the tip of this marker, turn and pivot to move around, and finally add the strip in red along the red poly edge. Similarly, then the second one, complementary one, is to delete a strip. So wherever you have the marker, you're deleting the transverse strip. And so as such, you can actually explore the coarse quad mesh, and then you have to define how you go from the topology to the pattern here for densification and smoothing and mapping to a circular boundary by exploring different strings that encode these different rules. So there's A, T, P, and D. You can actually move a marker around and add elements or delete them. So I will just highlight, for instance, the reading of that one. So you start by turning the marker, start adding a poly edge, do a succession of turn and pivots, then finally add the new strip, delete one, pivot, delete another one, etc. So here you have this small indices for special rules, but I won't dive into this. And as such, yeah, that was done manually, but an algorithm can actually compute this string, and knowing what's the input topology, the position of a marker, and what's your workflow, you can actually generate all this automatically. I'll just conclude with one example. So using a Fry Auto subbubble experiment, I was using this subfilm to find a minimal surface. So if we're not having a look at a subfilm, but actually a cable net to represent this, that's what you might get if you use the medial axis decomposition. And here you can encode different ones using the rules that I created to get these new topologies. And this is actually important because here you have this, don't have this continuous film, but this discrete structure. And if you run the values, if you do the similar form finding for all of these topologies, you can actually get a variation in the geometry after form finding, so up to 1/3 of the average edge length. So another point that which will change the performance of the behavior of your structure. Another point that topology matters. So here you have this geometry description with this vector encoding, and so that actually highlights the next research, which is combining this with state-of-the-art exploration optimization solvers. Yeah, so a brief conclusion. So for topology finding, I developed these 3 strategies. So one that's intuitive using geometrical objects. One that applies directly on the mesh topology using a graph structure or mesh structure. And one that goes at the low level of the string encoding and that opens for variety of applications. And so here we fulfill the initial objectives. So we focused on topological design of spaces. We provide these topology finding algorithms that we were able to combine with form finding, surface mapping, or shape optimization techniques. Benefit from the work done on topology optimization or field integration to inform the design, and we were able to freely select how we actually evaluate the performance of our topology. So what's next? As I said, to use machine learning, genetic algorithms to read all of these encoding strategies to provide the next generation of design tools. And I will just finish with showing that it actually expands to other types of systems. So I think that at the master, you're familiar with the work of Alison Grace Martin, and in a workshop with her, I had the chance to somehow to revisit everything, most of the work I did for quad meshes to triangulated meshes, and that way to be able to convert these into Kagome patterns, where you can see that instead of, which are a combination of hexagons and triangles, you could still introduce pentagons or quads or heptagons instead of quads, and then be able to explore these different systems, which are, here in that case, that cannot be described by quad meshes. Yep. Thank you for your attention. Looking forward for the discussion.
Thank you very much, Robin. It's been an amazing presentation. Some people are answering now. Okay, so does the people from the session wants to have a question?
Can I ask something?
Yeah.
First, it's very interesting, the topic and the approach and your study. So thanks for your presentation. I wanted to ask that what you're showing, like it's always you have like a certain level of input. Yeah, it cannot like on its own find the best optimal solution yet. No, like at some point it's relying on the different inputs of the either the code or the string or the like the places of manually you're inputting them, right? Just checking.
Yeah. So yeah, there's always this input, which is either coming from intuition or just a trial. And yeah, the first objective was actually to be able to encode all this. Even before running optimization algorithms, there was no means to actually describe these design spaces. So before searching for the design space, I had to create them. And so yeah, so to automate all this is part of future.
Yeah. So how far is like from being able to let it its own generate some inputs and analyze its own inputs and try different results? Maybe like I'm wondering, maybe more difficult, complex shapes, you might have an issue in you locating like certain points and inputs rather than letting it on its own generate.
Yeah, so there's one challenge is actually, or something important is actually, how do you get from this topology, which is abstract, it could be, you can move the nodes around, and how do you actually then, in that case, map it nicely to this circular boundary? That's pretty trivial in that case, but for a British museum, that's already a bit more complex. So indeed, if you have many openings, then it becomes can become a bit chaotic. But that's actually one strength of the middle axis decomposition, which gives you already a good starting point. And then, as you said, so if you have a good starting point, then you could have this. Then you can have something that runs and that will try to make a change, see how the performance changes, and then iterate like this. At the moment, I'm more interested in exploration because this problem is so complex that it's hard to automate. So that's what I showed with the self-organizing maps, which you actually use this exploration or automated algorithm that can structure your design space, provide you as a designer the information that you can read, and then you can work further. So it's more like co-designing with the algorithm and actually leaving the machine to do everything. It's probably easier to automate shape optimization or maybe density tuning than topological exploration, or at least the way things are now.
Thank you.
Okay, thank you. Robin, while everybody, if anyone wants to ask, but in the meantime, I have a couple of questions, but is this by any chance like I mean, I think it's a very, very interesting toolkit, like because you made the effort of bringing this into a very generic and abstract point of view, but is it available as a tool, as a tool set?
Yeah, so my, so like it's called Compass Singular, my library is it's open source.
So it's a part of Compass.
Yeah, so it's a package, it's a plugin.
Okay.
Based on Compass.
Okay.
Out of 4 or 5 methods I presented, I think that 3 are really robust, and I'm actually I'll be doing a workshop for AEG.
All right.
So that's also a target to have things as neatly packaged as possible, and then probably to wrap it up as a grasshopper toolbar if people don't want to actually go into the coding. So that's also part of the work to go from this conceptual or abstract concepts to a practical tool. So it's work in progress, but for medial axis at least, that's pretty robust.
And one thing, all this, as far as I understood, is mainly based on flat diagrams. So concerning, so I have 2 questions. Like, there is a good body of work on cleaning singularities on isotropic meshes, no, or like meshes not coming from Delaunay triangulations. I mean, can you reverse your algorithms instead of going like top down and use all these delete features to like clean the to reduce the complexity to the minimum possible singularities?
So all of these methods, they're not constrained to planar shapes. For the medial axis, you need to go to from a curved space to a planar one and move back. Then afterwards, if your input is a 3D mesh or design, you can still apply all of these operations in 3D. So, and if I understood correctly, so
yeah, no, my question was, I mean, can you? I mean, as I see the toolset is very good for the top-down approaches. No, like you start from coarse and you densify. But can you reverse it? I mean, can you have like when you have like something like very complex, full of singularities? I mean, can you like reduce this complexity?
Yeah. So actually, to do this, there are plenty of methods in computer graphics, but they just want to minimize the number of singularities. But for instance, if I mean, so when I'm given that pattern, for instance, that mesh, then what I do is that I find the singularities and these principal lines to get the coarse quad mesh, and that way I actually play with one object where you have the different layers. So you have this coarse quad mesh and this dense mesh, but there's this relation between, for instance, the edges in the coarse and the edges in the dense mesh. So that way, when you get this complex mesh with many singularities, you can still read it, and then you can apply rules to maybe delete some strips to reduce the number of singularities, and then that you can change it in the dense mesh as well. So you have this two spaces of dense and coarse meshes that change at the same time.
Okay. And when you were saying that obviously you can say you can input like non-planar elements. I mean, would it be easy for you to like directly? I think it's very related to the question from Rudy. But would it be easy for the method to locate singularities just based on the curvature features?
So, for instance, that's true. That so here for this example,
yeah,
I get the coarse mesh. I do the densification, and then, so in that case, there's no front panning. For this example, I'm mapping it on the target shape, and that's through relaxation that you get the singularities that slide on the shape. So if you were to have this part much denser, with relaxation, this would move inward. So there's also, there's topology, geometry, and there's this density in between, well, that might require some also some tuning or potentially some optimization. That's at least a nicely structured space. But for instance, if you get it from a curvature field, so you know for that specific requirement where your singularity should be. So imagine you get imagine you from a curvature field, the singularity should not be here, but it should be here. Then when you do the densification, then you can, that's what I did here, you base it on a target length that you don't get something a bit balanced. When you do the smoothing, the singularity will not move and you get still a nice density layout. So that's all dealt with density and geometry. So that could be completely tuned for the specific application.
Okay. Okay, since you are here, this is not like a very interesting question, but how do you do the grafting?
So the grafting, So actually, I'm using a Delaunay triangulation to find the topological skeleton. And for this node, singular node, there's a single face, which means that the face is adjacent to faces, and it has 3 points to the
all right.
So you can connect it to the.
Okay.
But if you don't know this, then it's basically the projection, the closest point, but that's a bit more expensive computation.
Yeah. All right. Anyone who has another question? Okay, so I think we can call it a day for this long session. So thank you very much, Robin. I personally have to appreciate like the good quality of the drawings, the good taste. I mean, everything looks very good and beautiful. So that's a super plus for the understanding on such a complex stuff. So I think it's like a pleasure to watch this type of presentation. So thank you very much. And I believe, I'm sure all the students have enjoyed it, and hope to see you next time soon in real